and welcome to the Further Maths Support Programme revision recordings. In this session we're going to be looking at MEI M2 and we're going to be looking at the centre of mass topic. So these are the basic ideas in centre of mass. You need to be able to find the centre of mass of a system of particles given the position and mass of those particles. You also need to be able to appreciate how to locate the centre of mass by looking at the symmetry of certain shapes. You need to be able to find the centre of mass of a composite body by looking at each of the parts of that composite body and combining the moments of each of the constituent parts to equate with the moment of the total mass. And you need to be able to use the position of the centre of mass in statics questions, equilibrium type questions. So let's take a look at a classic example in here. If you're going to be working through this at home, this is a good point to pause the recording and try working it through yourself. I'm going to be going straight into the solution. You notice here that we have this composite body that's made of a rectangular base, a vertical upright and a horizontal section at the top, and the masses and lengths of all of those shapes are given with reference to this horizontal x-axis and vertical y-axis here. The way I like to work through finding the centre of mass of a composite body like this is I like to set up a table of values. Please excuse my slightly wobbly lines here. So I will list the elements of the composite body in the left-hand column here. So this is the rectangular base, this is the upright, and this is the horizontal section at the top. And we also list the total in here. We want a column for mass. The mass of the base is given in the table here as 15 kilograms. The upright has a mass of 3 kilograms, and the top rod there has a mass of 2 kilograms, giving a total of 20. I'm then going to put in an element in the next column which looks at the distance of the centre of mass of each section of the composite body from a particular axis. So the first version I'm going to put in here is the distance of the centre of mass of each of the objects from the axis OY. So PQRS, that rectangle at the bottom, that's going to be 20 by symmetry. The vertical is actually on the axis, so it has 0 distance, and the horizontal section at the top, again using symmetry, is going to be a distance of 25 away from that axis. Now looking at the distances from the horizontal axis to get our vertical coordinate of the centre of mass. The flat base obviously lies on the axis, so that has a distance of 0, and we can complete the other distances just by reading off the diagram. Okay, so the basic method for this is to say that the sum of the moments of each of the elements is equal to the moment of the total mass of all of the elements. So let's work that through. We're going to take moments about the vertical axis first of all, so taking moments about an axis along OY. Moment, in this case we're going to use mass times distance. Technically moment is force times distance, which should mean that we're using weight, but because the component of the weight, which is given by g, the acceleration due to gravity, that would cancel out all the way through, so we ignore it anyway. So working out masses times distances, first of all for PQRS, the moment for that one is going to be given by 15, the mass times the distance from the axis. And for OA we're going to have 0 moment, so I'm not actually going to include that in here because it lies right on the axis, so we're not going to bother with it. This is the moment then for AB, the section at the top, 2 times 25, and that's equal to 20 x bar, 20 being the total mass of the whole system, and a little bit of work on that fairly swiftly gives our value of x bar as being 17.5. We can take moments about an axis along OX in exactly the same way. So the base has no moment because the distance of its centre of mass from the axis is 0, so I'll leave that part out. For OA, that vertical rod, the moment's going to be 3 times 100. And for the top section there, that's going to be 2 times 200. Again, mass times distance. That's going to be equal to 20 y bar, and we can simplify through and get y bar is 35. So the coordinates of the centre of mass of the stand there, given by 17.5, 35. Just taking a quick look at the allocation of marks there, you would be given a method mark for the method of taking moments. You'd have a B mark, an answer mark for giving at least some correct values in this section here, an answer mark for gaining the 17.5, and an answer mark for y equals 35. Okay, so going on from there, we've now got this extra object which is attached to the rod AB at a distance of 40 centimetres along. So we add this object in here that's got a mass of 5 kilograms, so a weight of 5g newtons. And we're going to show that the coordinates of the centre of mass of the stand with the object added are at 2268. Now we could go back to scratch and start with our table again, because we could just include this extra element in the whole calculation. But actually we don't need to, because we know the total mass and the location of the centre of mass of the original combined composite object. All we need to do is take moments about OY again, taking the whole of the original composite body as one chunk. So that total mass for the original section was 20. We worked out in the first part of the question that the location of the centre of mass was 17.5, 35. So 20 times 17.5 gives the moment of the original composite body. We're going to add to that our 5 kilogram mass multiplied by its distance from the axis, which we're told is 40 centimetres. That's going to be equal to the total mass, which is now 25, multiplying our new location of centre of mass, and I think we can show that gives us enough information in there to be able to say that x is indeed 22. Similarly, taking moments about OX in exactly the same way, 20 times 35, that's the moment for the total original composite body, and 5 times 200, that's the moment for this new particle, this new object that's been added in. That's going to be equal to 25 y bar, y1 bar as I've called it here. And again, that should be sufficient to show that y1 bar is 68. And there's a method mark for taking moments there, and an E mark for showing the result that was given in the question. Okay, so again here, if you're working on this at home, this is a good time to pause and see if you can work it through yourself. As I say, I'm going to continue with the solution. So the stand's going to be tilted about this edge PQ here until it's on the point of toppling, and the angle through which it's tilted is going to be called the angle of tilt. So we tilt it about PQ, we tilt it about edge QR along here, and we tilt it about edge RS. And it's asking you to make your method clear and determine which edge requires the smallest angle of tilt. Now I find this easiest to do if we look at an elevation. So the first thing I'm going to do is just do a little sketch of a side elevation of our shape here. And this is O, this is A, this is B. This is just a simplified version. So a side elevation here. We know that the centre of mass is located somewhere around about here. I'm going to call that G. And we know that that centre of mass from the previous part of the question is 22 centimetres across and 68 centimetres up. Apology, diagram not drawn to scale. Now, when the object is tilted about this edge PQ here, O becomes the point of contact with the surface, and G, just as the object topples, we will have the weight of the object passing through both G, obviously, because that's where the centre of mass is, and O. So just as it's about to topple, the setup will be that this arrow that I've drawn here will be the vertical. So the angle of tilt, if you can imagine this object is being tilted until my line GO is vertical, so the angle of tilt in this case is this angle here, which I'm going to call theta 1. So that's the angle of tilt in that section. If I if this time I'm going to do a front elevation, this is when it's going to be tipped about edge QR. So if this is kind of edge QR from the front on here, this point up here is A, this is O in here, and you know that the centre of mass is going to be somewhere around about here at a distance 68 up from the base. This is 15 centimetres because the width of the rectangle here was 30. This is a 15 centimetres here. If you're going to tip about QR, then just as it tips, this line becomes the vertical. My apologies for the wobbling there. Okay, so our second critical angle, if you like, theta 2, that's the angle that we would tilt through in order for this line to be vertical. For the third possibility, if we're going to rotate about RS, I'm actually going to go back to my original diagram here. If we rotate around RS, this becomes the point of contact, and this arrow here becomes our new vertical, so our angle of tilt in this particular case is shown here. That's going to be my theta 3, my third critical angle in here. Okay, so let's have a little think about what makes that angle the smallest. So we're looking for the smallest possible theta in this case. Now you can see here that theta 1, oops, not Q, sorry, the tan of theta 1 is 22 over 68, just using that right angle triangle with the distances in from our centre of mass calculation. The tan of theta 2 is 15 over 68, and the tan of theta 3 is going to be 18 over 68. That 18 is this distance here. It's the 40 minus 22 distance between the centre of mass and the front edge of the rectangular base. So you can see here that the angle with the smallest tangent is theta 2 here, and if it's got the smallest tangent in this case, because these angles are all acute, that means that it's got this must be the smallest angle. So we can conclude here that theta 2 is the smallest, and what that means is that edge QR, because we were tipping about edge QR when we found theta 2, edge QR requires the smallest angle of tilt. Okay, and a quick look at the mark scheme on that one, noting that you've got that you need to look for the smallest angle, or the smallest distance, if you like, is a method mark in here. Being able to calculate at least one of the distances gives you a B mark, and being able to calculate all three gives you another B mark, and explaining that that means that QR is the correct edge to tilt about gives you the final answer mark in that case. Okay, so we're going to change the situation a little bit now. Again, if you're working on this at home, please do pause at this point and have a little go at the question yourself. So we're changing how this is behaving. The small object has been removed. I've got a light string attached to the stand at A, and it's pulled at an angle of 50 degrees to the downward vertical in the plane OXY to try and tip it, this time around this front edge RS here. So I'm going to draw a side elevation of this particular situation, because all of the forces, etc., are acting in 2 dimensions here. We're told that the string is at an angle of 50 degrees to the downward vertical, so let's draw the string in there. This is my 50 degree angle in here, and I'm going to call the tension in the string T. We can locate some other points of interest here in the diagram. Our centre of mass is here at G, where we know this distance is 22 and this distance is 68 from the earlier part of the question. Now it says that the stand doesn't slide and the stand is just about to turn around the edge RS. So in our 2D diagram that we've got here, that means it's about to turn about this point here at the edge of the rectangle. That means that all of the contact forces can be considered to act through that point. So we're going to have a vertical reaction force upwards here, normal contact force, and there must be a frictional force, and that frictional force has to act in this diagram right to left because the component of our tension in the string here is acting left to right, and we need our frictional force to cancel that out. Oh, I'm sorry, I didn't put the weight in here. I marked my centre of mass, but I need to put in also the weight that's due to the mass of the whole object, which is going to be 20 newtons. So we've got 4 forces that we need to consider in this diagram. If we're going to be finding the tension, we've got 4 forces, and at the moment 3 of them are unknowns. We don't know the reaction force, we don't know the frictional force, and we don't know the tension in the string. So it's going to be sensible at this stage to choose a technique which avoids using as many of the unknowns as we can get away with, and so that's a good reason then to take moments about this point here, that meaning then that we can ignore the frictional force and the normal reaction because they both act through this pivot point. I'm going to call that point, I can't remember what I'm going to call it. I'm going to call it P for point. Oh no, I've already got a P, my mistake. Let's call it C. Okay, so that point C there, I'm going to take moments about that point C, or an axis through C. I'm just considering this diagram in 2 dimensions at the moment, just to simplify things down. So taking moments about that point C there, we can ignore the friction and the normal reaction, and we need to take moments in a clockwise direction and an anti-clockwise direction. Now, the 20G that we've got here, that one's fairly easy to take moments about, and I hope you can see that that acts in an anti-clockwise sense around C. So I'm going to put the anti-clockwise moments first of all on the left-hand side. So my 20G is multiplied by the distance of its line of action from the pivot, which is going to be 18. No, it's not, my mistake. I've put an incorrect measure on that diagram. Excuse me just a moment, bear with me. Sorry, this is the version with the particle removed rather than with the particle in there. So we're going back actually to our original measurements where this was 17.5 and this was 35. Sorry, my apologies there. Okay, so as I say, taking moments for the mass here, we've got 20G times 40 minus 17.5 is going to be our distance, horizontal distance from the pivot there, which is going to give me 22.5. And we've then got a couple of components of T to think about. Now, if we split T into perpendicular components, one of them will act vertically downwards and hence in an anti-clockwise sense around C. The other one will act horizontally left to right, and that's going to act in a clockwise sense. If I'm totting up all of the anti-clockwise moments, I need to include a component of T, and that's going to be T cos 50 multiplied by the distance of the line of action from the pivot, which in this case is going to be 40. So that is the downward component of T, T cos 50, multiplied by that horizontal distance there, which is the 40. So that's all my anti-clockwise moments. In the clockwise direction, we have just our component of T multiplied by its distance from the axis, which is going to be 200 centimeters. So that's the T component horizontally here multiplied by that vertical distance, which was 200 from the original diagram. And then we can do a little rearrangement of that. So I'm going to get 20G times 22.5 equals t, and I'm going to factorise here, 200 sine 50 minus 40 cos 50, and that now is ready to go right into your calculator. That gives you t equals, and your calculator reads something along the lines of 34.588, etc. So we say that t is 35 newtons to two significant figures. Oh, obviously if you want three significant figures you can go to 34.6 newtons for three significant figures. Okay, quick run through the marking there. You'd have a method mark for an attempt to take moments about an axis along RS, which is what we've done here. You get a B mark for working out some numbers connected with the components of the tension here, an A1 for getting that correct, and a B1 for the answer in there, and then two A1 marks just to tidy that one up at the end there. Okay, so moving on to a second question here. Now I'm not going to work through the entirety of this question, but I wanted to show you that this is similar to the earlier part of the first question that we did, but it highlights a particular feature of some of the questions that you'll see on centre of mass here. So you notice in this question we have a lamina here, KLMNOP, and made from uniform material with the shown dimensions. So if we were going to locate the centre of mass of this one, I would probably want to split it up into two sections, two rectangular sections, by cutting it perhaps across here, and I'd set up my table of values just as I did in the first part of the question, showing each of the sections, showing the total, and showing the masses and distances from the two axes for each of those sections. If I do that, I end up with the location of the centre of mass for this section being 2644. And it's worth having a quick check just to make sure that that's sensible. You would expect the centre of mass to be a little further across than halfway through the 40 here because of this additional section on the end, and 44 seems reasonable. It's just a little above the dividing line here. That seems like a reasonable place to put it. So this is the answer that you get if you consider this shape as a lamina. In the second part of the question, the shape is similar, but instead of being a lamina this time, we're dealing with a wire, a heavy wire, which is bent into the shape of part of the perimeter of the lamina. In this particular case, the centre of mass is going to be in a different place. Although the shape looks similar, the centre of mass will be in a different place from the centre of mass for the lamina version. And what you need to do is consider each of the elements of the heavy wire in turn. So you could look at KL, LM, MN, NO and OQ all separately and sum them together, etc. This time you get a completely different location of centre of mass. You can see already here that X comes out at 23.2, and the Y coordinate using that method comes out at 40.2. So you can see, just comparing that with the previous slide, that does give quite a different value using rods or heavy wires instead of the original lamina type model. The question then produces a hanging section, so the wire is freely suspended from Q and hangs in equilibrium. So we need to draw a diagram indicating the position of the centre of mass of the hanging wire and calculate the angle of QO with the vertical. Now, personally I find it fiddly to turn the diagram to make it vertical, so here's a little sneaky trick. You know that the centre of mass is located at 23.2, 40.2 from the previous part of the question, so that's going to be, I would suggest somewhere around about here. I'm going to label that G, and then you can draw in a vertical from Q through G, because you know, you know that G must sit directly below the centre, the centre of mass must sit directly below the location of the pivot point. So that line there is the vertical when it's hanging in equilibrium, which means the angle that we're looking for, that QO makes with the vertical, is going to be this angle here, theta as labelled. And we can look at this little right angled triangle here. So we can say tan of theta in this case is going to be that horizontal distance, which we know is 23.2, over this vertical distance here, which is going to be 110 minus 40.2. And popping that into your calculator gives you theta is 18.4 degrees to 3SF. Okay, so now again the question extends the methods that we've looked at already. You can see here that we now have this sort of three-dimensional shape rather than a two-dimensional shape as we were dealing with before. The sort of middle part of this bin shape is modelled by the wireframe that we looked at in the second part of the question, and the ends now are modelled by the laminar section that we had right at the beginning of the question. So essentially moving the wireframe into two dimensions like this doesn't change the location of its centre of mass, or the distance of its centre of mass, at least from the x and y axes. Obviously it will push it back in that third dimension, but it doesn't change it in the two-dimensional model that we're using in this situation. So again, now we're going to be using the ideas that we had in the previous sections of the question. So we can look at, I'm going to look at the centre section, the ends, and the total. Put in my mass column. So we know that the solid bit in the middle is 7 kilograms. The ends altogether are going to be 3 kilograms, and the total therefore is 10. The distance from OY for each of these sections, we know that the centre has a distance 23.2, that's from the wireframe model. Each of the ends has a distance of 26, that's from the laminar model, and we're looking to find x bar. Similarly, for the distance from OX, we've got 40.2 for the centre section, 44 for each of the ends, and we're looking to find y bar here. So we can take moments. We're going to be looking at, I'm just going to do this in vector form here just to show you that this can be done. So taking moments about each of the axes, but doing this in combination. Mass for the centre section times distance from the axis, just using column vectors for the locations of the centres of mass. For the end sections, we've got 3 times 26.44, and that gives us a total then 10 x bar y bar, and we can work through each of the lines in turn, and that gives us an x bar 24.02 and a y bar of 41.34. So I think that's a really nice question for highlighting how differently objects behave depending on whether they are laminae or whether they're modelled by rods, etc. Okay, so thank you very much for watching. There are other videos available on the same site. I hope you'll take the time to visit www.furthermaths.org.uk and look at the other things that we have available on there. Thank you very much. Goodbye.